Everyone, I am Annika Znab, Director of Earth Science at EC, and it is my great pleasure to welcome today Danièle Hauser for a lecture on the CFOSAT mission. So I will briefly introduce Danièle. Danièle is a senior scientist at the Centre National de la Recherche Scientifique, CNRS, in France. She works at the laboratory called Atmosphere Milieu Observation Spatiale, l'ATMOS, in Paris, a laboratory that she directed until 2014. Danièle began her research career in the early 80s in atmospheric science using remote sensing techniques. At that time, she worked on the properties of clouds and precipitation, and on atmospheric dynamics and thermodynamics in a cloudy environment. And since the early 90s, her research is focused on the physical processes that take place at the ocean surface, and more particularly on matter and energy exchange at the air-sea interface, driven by wind and waves. Among others, she studies the generation and evolution of waves, as well as the turbulent fluxes occurring at the air-sea interface and the driving role of waves on these fluxes. She is an expert in designing and developing new observing systems based on remote sensing techniques with the objective of monitoring ocean surface parameters such as wind, waves, and salinity. She is a principal investigator of the CFOSAT mission, a joint mission between China and France, launched in 2018, that currently provides unique observation of surface winds and ocean waves. And this mission is certainly a game changer in this domain, as we are going to listen now from Danièle and learn more about this mission and this application. So I stop here, and Danièle, the floor is yours.
Thank you very much, Annie. So I try to share my screen. So is it okay now? Do you see the screen?
No, we still don't see.
Not yet.
Oh, yes, I have to share first. Excuse me.
Okay.
Okay. So the title of my good afternoon or good morning, I don't know, wherever you are. So the title of my talk is about wind and waves on the ocean surfaces. And this is to present recent results from the China-France Oceanography SATellite, so-called the CFOSAT mission. So I present this talk, but you will see that I present many results which have been given by my colleagues from the science team, which has been organized to share all the data information on CFOSAT. So the outline of my presentation is the following. First, I will give some information about why observing wind and waves at the ocean surface, then why and how measuring wind and waves from space, and then I will focus on what is new with the CFOSAT mission in this domain. So I will present the specificity and originality of CFOSAT and present you the first results and scientific breakthrough obtained with these observations, and give some perspectives about analyzing this data set. I will also say a few words about the use of CFOSAT observation for operational use and applications, and I will conclude. So first, why observing wind and waves at the ocean surface? This is just beautiful pictures, nothing to say. I come back to the major role of the ocean. So this is very general information. Maybe many of you know this. First, the ocean represents 70% of the globe surface. They play an important major role on the climate system because they accumulate, transport, and redistribute heat from or to the atmosphere, and it's a major reservoir for the water and gas budgets, and in particular the CO2 budget. Also, oceans are very important in our societies because more than 50% of the population live at distances less than 100 kilometers from the coast, and many inhabitants are in regions that can be flooded by ocean water. Oceans also represent important resources in terms of biological, mineralogical, or energetic resources. And it's also very important in the economy because it's a place where there is transport, exploitation of resources, tourism, etc. And finally, the oceans are the place where natural hazards take place, also like tropical or mid-latitude storms and flooding in coastal areas, and also the problem of erosion in coastal areas. Now, if I focus more on wind and wave in this coupled ocean atmosphere system, so you probably all know also that wind is a major parameter in the ocean atmosphere for the ocean atmosphere exchanges. It plays a role in the near surface currents, in the heat exchanges between ocean and atmosphere, in the evaporation at the surface. So it contributes to the global water cycle. It also plays a role in the ocean mixing in the upper layers, principally through waves, the formation of waves. I will talk about this later. And wind also transports marine aerosols. And finally, wind generates surface waves, which propagate eventually outside their zone of generation and impact the ocean and the atmosphere at remote distances from where they are generated. Now about waves, so these waves, by waves I mean wind-generated waves. The first thing to say is that waves modify the surface roughness, and hence they modify the drag of the wind at the surface. So eventually this impacts the ocean circulation, because ocean circulation is partly forced by this drag. Second, during their growth, waves modify the quantity of the momentum flux absorbed by the ocean. So it also impacts the ocean circulation, and in some cases, the atmosphere also. Then breaking waves generate turbulence. So it impacts the mixing in the upper layers of the ocean. And in return, it impacts, this mixing impacts the sea surface temperature and the heat fluxes, the heat exchange between atmosphere and ocean. Also, waves induce surface currents, and which we call them Stokes drift, and mesoscale circulation, which are called the Langmuir circulation, and explains sometimes some rolls that you can see close to the surface. Also, wave properties, that means wave height, wave direction, and wavelengths are modified by the strong currents which exist in the ocean, like the Gulf Stream, the Kuroshio, the Agulhas current, and waves wave exchange energy between the currents and the waves. There is an exchange of energy. In addition, as shown in the impact, you can hear me, yes? The polar region, they have an impact in the destruction and generation of the ice, of the sea ice. They also impact the aerosols in the marine and for condensation cloud nuclei. This is what the continuing of this effect of waves. So waves impact the CO2 exchanges also, because they inject bubbles into the water. So this changes the efficiency of CO2 exchange between atmosphere and ocean. And as I said, they generate aerosols, which eventually serve as cloud condensation nuclei. Finally, I would like to mention that wave properties, height, direction of propagation, are modified by the climate change, as mentioned by, for example, by the last IPCC report. This is due mainly to the changes in storm intensity or storm tracks, and this impacts the upper ocean mixing, the cold surge, and erosion. So outside these domains of geophysical domain, the importance of wind and waves is also demonstrated for ocean users because observations of forecasts are essential for security and operations at sea. It's evident that it's very crucial information for ship routes, for supporting fishing, oil industry, and marine energy industry, and also to protect the populations and the goods in the coastal areas. And finally, for the numerical point of view, observations are required for wind and wave numerical forecasting to validate the model and to assimilate observation in models so that they keep a good performance. Waves also are important in the marine environments because they directly impact the sediment transport in the coastal zone, the coastal erosion, and the drift of pollutants, and also the biosphere. So wave parameters are key to study and model the evolution of this environment. Now, why and how measuring wind and waves from space? So this is a scheme which shows the different scales, temporal scales in vertical, and spatial scales in horizontal. You see on this scheme that there are different means existing depending on the scales you are interested in. If you are interested in a short temporal and spatial scales, and you have radars on the coast, you have fishermen vessels, you have gliders, you have buoys. But if you go to the regional and oceanic basin scale and also long time series, then the only mean is to deploy space observations. Of course, you have also buoy or ships, but it does not cover all the scales. So it's really useful to have space of observations. This is an illustration of this problem. Here on the left is a map of a large part of the buoy network, which are deployed in operational way to measure atmospheric pressure and some of the oceanic parameters. They are mainly deployed to measure pressure, atmospheric pressure, air and water temperature, wind, and some of them are deployed, but not all, to measure the waves and sometimes salinity also. This is a type of mooring, classical mooring, which is deployed for these measurements. And you see it's not a very robust thing. And so they are deployed mainly close to the shore, except in some tropical areas. And so also this limits the information that we get about wind and waves far from the coast. Another way also that exists is measurement from ships equipped with automatic measurements, but again, the coverage is not very good. And now if we go to space coverage, this is an example of a space coverage with two satellites dedicated to, which give information on wind and waves, which are the Sentinel satellites here. And so you see that within 1 week of measurements, the coverage is really greatly improved. Now, what sensors in space for wind and wave measurements? Typically, the main technique which is used, it comes from the microwave domain. This means radio frequency waves from typically 1 to 35 gigahertz. In this domain, we have two categories of sensors. The active sensors, which means radars, which transmit and receive signal backscattered from the ocean surface. Typically, these sensors are used to measure, that means wind speed and in condition wind direction, ocean waves, sea ice coverage, and in certain conditions, sea ice type. Passive sensors, that means it's a second category. It's sensors that just receive natural emission from the environment and in particular from the sea surface. And they are used to measure wind speed, sea surface salinity, sea ice coverage and concentration, and in some condition temperature also. So this is the two main categories. And now I take a few moments to explain how we characterize waves at the ocean surface. So you first have to realize that when we talk of waves, in fact, it's a superposition of waves of different scales, that means different wavelengths, or equivalently different frequencies of oscillation. You see on the left picture that it's very common that waves of different scales superpose on the surface. And to represent this information, an easy way to represent this information is to represent them by the directional spectrum of the waves. So what is this direction spectrum? It's a way to represent the height, or equivalently the energy of the waves, as a function of the wavelengths and as a function of the direction of propagation. And on the right-hand side here, you have a plot which shows a polar plot with a color which shows the energy or the height of the waves. The direction, the angle from the top of the figure gives the direction of the waves, and the position of the colors gives the wavelength of the waves. The closer to the center, the longer are the waves in this typical plot. And in this example, the energy is in different domains. One at very long wavelengths, which characterize what we call the swell, and one which is at shorter wavelengths and aligned with the wind, and this is what we call the wind sea. The total the spectrum is also characterized by these main parameters, among which the significant wave height, which characterize the total energy of the waves. And classically, we also characterize the spectrum by the peak wavelength and the peak direction, which define the type of wave system. Indeed, you have to know also that the wave evolution is governed by input of energy by the wind, by nonlinear interaction between waves, and by dissipation, mainly given by the breaking and by the friction at the bottom of the seabed. And also wave energy propagate like any waves. And one important thing to know with the waves, ocean waves, is that they are dispersive, and that means that their propagation speed increases when the wavelength increases. This means that they can escape from their generation zone, and in this case, they are called swell. And so you can find swell in areas where there is no wind, whereas in the area where the wind is blowing, you have what we call the wind sea, which is waves generated locally by the wind. On the right-hand side, you have an example here of the evolution of the wave spectrum. Here, it's omnidirectional spectrum. That means it's only as a function of frequency, not distance, not direction. And it's a different spectra from going from the coast to the open ocean in a region affected by offshore winds. In fact, it's in the Mediterranean Sea here, and this was observed with an airborne radars. And on the right, excuse me, it's the one given by a numerical model. So you see that how the wave spectrum transforms from the coast to the open ocean with peak frequency, which is evolving from high frequency to low frequency, which is equivalent to say that it's evolving from small wavelengths to long wavelengths. And also the energy is transforming, is increasing along this fetch, what we call the fetch, which is the direction and the distance of action of the wind. Now, how can we measure wind and waves from radar systems, and in particular from the space? We distinguish here 3 regimes depending on illumination angles. That means the incidence, the angle between the satellite nadir and the point of measurements. We have typically 3 kinds of geometry. The first one is a nadir incidence. That means 0 degree with respect to nadir. In this case, the backscatter from radar measurements is mainly specular. This means that the reflection is governed by the slopes of the waves, and at the first order, this statistic of slopes is related to the wind speed. And so this is a principle used by altimeters, which provide the wind speed. And also the shape of the echo, which is backscattered by the surface, is modified by the long waves. And this is the way it is used to estimate the significant wave height from altimeter measurements. Also, this technique is used more or less to estimate the wind speed from a localization system like GNSS. The second type of second regime of backscattering is off nadir. That means incidence angles larger than typically 25 degrees. In this case, the backscatter is dominated by the Bragg waves, which are the short waves, which are sensitive to, very sensitive to the wind. They respond very rapidly to the wind. And in this case, the backscatter is mainly governed by these short waves, and there is only a weak effect of long waves, which are within the footprint of the instrument. So this is a principle used by what we call the wind scatterometers to estimate wind speed and wind direction. And finally, there is an intermediate regime, which is for incidence between 0 to 20 degrees about, which is mixed between both. That means that it's there are additional impacts of the long tilty waves as represented on this scheme. So there is an additional impact in addition to the specular response which occur when we are looking close to nadir. So this principle of measurements is used by synthetic aperture radars and also by the SWIM instrument, but with our slightly different geometry. I will explain just after. So this means that it's possible to image the long waves, typically waves longer than 50, 70, 100 meters, it depends on the instrument, within the radar footprint, the spot at the surface, by choosing this geometry, which is close to 0 degree. So what is the CFOSAT mission? So what are the specificity and originality? The first specificity is that there are two instruments carried by this satellite on the same platform for measuring wind and waves simultaneously. So it was a choice of this mission to really focus on wind and waves and to have a dedicated mission for wind and wave measurements, considering the important effects that I mentioned at the beginning. Then the instrumental concept of these instruments are new. First, there is a wind scatterometer. So wind scatterometer already exists in space with many missions, satellite missions, but this one has a new geometry. I will not enter into details, but it's a fan beam antenna at medium incidence and scanning over 360 degrees. So it's the first time that this concept is in orbit with this configuration, which is both fan beams, that is a very wide beam aperture
Danièle, we lost you.
Wide swath and scanning. Can you hear me? Hello?
Yes, now, yes, but we lost you for a few seconds.
Okay. Do you see my presentation?
Yes, it's okay. So you can continue. Okay.
So I was saying that SWIM is also a new concept. SWIM means surface waves investigation and monitoring. We call it a wave scatterometer. It has an altimeter mode, like altimeters looking at nadir and near nadir incidence from 2 to 10 degrees. And it also scans over 360 degrees in the around the vertical direction. And this was designed to measure the directional wave spectra, as I explained before what it is, and also wind speed and significant wave height from the nadir beam. So this concept is entirely new for space observation. This is one of the originality of CFOSAT, although it was already deployed for airborne measurements. Another originality is that it is the first scientific cooperation between France and China in the spatial domain, in the space domain. We know that another one will follow soon in astronomy. This is the characteristic of the satellite. It's the polar orbit at 520 kilometers, sun-synchronous and 13-day orbit cycle, but it's detailed. The instruments are carried by a Chinese platform, and it was launched from China on October 29th, 2018. Now more details about the instruments. So I come back to the SWIM instruments, which means surface wave investigation monitoring. It was designed and manufactured by France under a cooperation between CNES and Thales Alenia Space. It's a Ku-band radar, that means functioning at about 13 gigahertz. It has a geometry which is explained here. It looks at nadir vertically like standard altimeters, and I know there has been a lecture on altimeters during EC seminars. And it has also off-nadir illumination from 2 to 10 degrees with a sequential mode of illuminations. That means that all antenna beams scan in azimuth here. It means around the vertical point, and also illuminate successively the surface from 0 to 4, 6, 8, and 10 degrees, and then again 0 to 4, etc. The beam at the surface is 18 kilometers. That means large enough to see the modulation due to the long waves in the radar backscatter signal. And the total area here is a radius of about 19 kilometers in radius. The geometry of CFOSAT is described here, and the characteristic is described here. See, it's also a Ku-band radar, also at the same frequency, transmitting frequency. Here, the incidence, because it's a scatter method, the incidence is larger because it is where these instruments are most sensitive to measure the wind, both the wind direction and the wind speed. It has a wide swath at the surface, about 1,000 kilometers. So this is a swath scanned by the instrument, and which illuminates the surface over an area of about 1,000 kilometers. This is how look like the visible part of the instruments. That means the antenna systems. This is a SWIM antenna system. You see it's a very big one, 2 meters high. The parabol here is directed towards the surface because the signal is transmitted and received through these parabols. And this system is a rotating plate where the feed horns of the radar are implemented. There are 6 feed horns for 6 incidents, 0, 2, 4, 6, 8, and 10 degree incidents. So it transmits and receives signal towards the parabols, and the parabols receives and transmit from the surface. This is a SCAT antenna system, which is more classical. It's 2 plane antennas. And here is how it is implemented on the platform. So this is a SCAT system here, SCAT antenna, and the SWIM antenna here. And you see it's a very big antenna. Now, what are the main parameters estimated from the SWIM measurements? The first one is the significant wave height and the wind speed along the track, along this red arrow from the nadir beam. And this is similar to other altimeter missions. It's rather classical. But what is not classical is that in addition, we have information on wave spectra in these boxes on each side of the track. So it's about 70 by 90 kilometer length cells in which we can have the directional spectra of the waves. That means, as I mentioned before, the wave height as a function of wavelength and direction, with, however, an ambiguity in direction of 180 degrees. That means that we cannot know what is the direction of propagation where is this direction or this one. The way we estimate the directional spectra from the signal, radar signal, I will not go into details, but just mention that for that we use theoretical formulation which relates the variation of the backscatter signal and the slopes at the surface, because the signal at this incident is sensitive to the long slopes of the waves. The main challenge in this inversion method is to eliminate the what we call the speckle noise. Speckle is a noise in coherent systems. And well, just I mentioned that this is the main difficulty, and this is a reason why you see some noise in this representation of the wave spectrum from SWIM. And we try to eliminate it in the post-processing at the ground processing. Now for SCAT, the main parameters are rather classical. It's wind speed and wind direction in about in wind cells of about 25 kilometers. And for that, we transform also the radar signal into a geophysical variables, which is the wind direction and wind speed. This is done by using an empirical model which relates the backscatter intensity and the wind, and which has been established for various previous missions, wind scatterometer missions. So now I'm going to present a selection of results which comes from myself or colleagues from the science team. And we have exchanged recently with an online meeting which took place last week. And previously we had a meeting which was to discuss the first results on the validation of this data in China in 2019. The first step for the SWIM instrument, for the wave, which provides the wave information, was to validate the observation, to improve the inversion method, and to provide new data set. As I mentioned, this instrument is completely new in space, so we had to took some time to validate this. And this was done using different approaches. One of them is to compare it at the global scale with numerical wave model outputs, and this is illustrated on the left here with comparison of the wave parameters extracted from the measurements, significant wave height, dominant direction, and dominant wavelength from the SWIM instrument and from the model here. And the conclusion is that the consistency was overall good, and since this study we increased these performances. We also made validation using in situ data, as illustrated here, for example, with a comparison of a time series of significant wave height and wavelengths of in situ data in black and different estimates from SWIM in the color. I will not go into details. So you see that the time series of wavelengths and also wave height is rather good agreement between both time series. And we also estimate the performance by comparing with a network of buoy, which is NOAA, American network of buoy data, but which are usually more coastal information, and compare the different parameters between SWIM and the buoy. So we concluded that there is another good consistency, that the waves are well detected in the 50 to 500 meter wavelength range in agreement with what we had specified, and with, however, some limitations when waves of low energy propagate along track because of speckle perturbation, as I mentioned before. And for the first time, we could provide continuous map at a global coverage of these parameters: wave height, wavelength, and wave direction. And this is really new because the other systems that we have in space, and in particular the synthetic aperture radar, does not provide a global coverage as it was possible here. This is maps which are plotted for a 13-day period. Another result was obtained by an analysis of the altimeter data. So this is more specialized for persons who are aware of these nadir observations. So for this nadir observation, we improved the parameters which are retrieved from the signal with respect to classical method. And this was done because we had the opportunity to develop and validate an improved method called the adaptive retracking method. I will not explain the method, but just mention the results. The results as we have is that we have less noise in the estimation of the along track variation of significant wave height. So it means less noise on the parameters of the retrieved from the echo, in particular significant wave height. This is illustrated here by fluctuation spectrum of significant wave height along the track. So it's a spectrum as a function of wave number of fluctuation. This is in orange a classical algorithm, and in blue the new algorithm. And from this plot, you can see that the level of noise is decreased when we use a new algorithm to 22 centimeter instead of 36. Also, with this new altimeter, we could evidence that we can better identify the sea ice and the variations of sea ice in the polar regions, as shown here. And this is the backscatter coefficient retrieved from the new algorithm, and this is from the classical one. So you see structures in the sea ice region which are not apparent when you use the classical algorithm. And finally, we validated also the main parameter, which is a significant wave height, by comparing to the more classical retrieval by existing altimeter satellite here by JSON3. So this is a comparison of significance between both satellite, and the comparison is very good with differences, root mean differences of less than 20 centimeters. The colleagues from China also validate the scatterometer observation. So this is a comparison of wind intensity and wind direction between the CFOSAT scatterometer retrieved information and the ASCAT, which is on the METOP, European METOP satellite. So you see that the comparison also is very good. And on the right, it's a comparison with buoy observation for the same parameters, wind speed and wind direction. So we are very confident with this data. Now I go more into details about the results obtained on the geophysical part of the analysis. First, I present results very briefly on an assimilation study which use the full observation, the full information given by the SWIM radar. So I first recall that assimilation is a numerical way to constrain numerical prediction models by observation, so that the models does not depart too much from observation at a certain time. And what is new here is that we have used the spectral information, that means the wave spectra, not only the wave height, because wave height is classically already used in assimilation schemes of the models, but here we use the spectral information. And this study was done here to specifically on the Southern Ocean case, where very high wind, intense wind and waves are observed all the year, and here it's in spring. The results are that we could show that only the assimilation of spectral information, that means wavelength and direction of the waves, corrects at an appropriate level the error in the wave height of the model prediction. And this is illustrated on the right, where you have the bias, so the error of the model compared to satellite observations, which are not used in the assimilation. On the top, when the assimilation is done with wavelength and wave direction, in addition to significant wave height, and on the bottom, when it's done only with wave height information. And so it's difficult to see the details, but you can trust that really the scores are really better when we assimilate wavelength and direction. So it has an impact also on the wave height predicted by the model. And we explain this by the fact that in these regions where the waves are very strongly forced by the wind because of the very high winds condition with storms which are lasting long, the model tends to maintain the wave growth for too long time and tends to produce too high significant wave height if we don't assimilate data. And when this assimilation is done, so it's better if we assimilate spectral information than only a significant wave height. And this is important for future studies also because now wave models are frequently coupled to ocean models because this coupling brings many information on the and corrects information in the mixed oceanic layer because the wave development governs the turbulence intensity in the mixed ocean layer. So it's very important for the future also of ocean modeling. Another remarkable result is about wave spectra properties. And what we have studied here is frequency and directional distribution of the wave spectra. So I remind you what is this wave spectra with these schemes here. So what we have studied is the frequency spread of the spectra. That means how the energy is distributed in frequency. With two parameters here mentioned here, the sigma f, which comes from the Blackman and Tukey theory, and what we call the Goda parameter, QP, which measure a sort of pickedness of this parameter, of this shape. We also studied the directional spread. That means the way the energy is spread around the peak of the spectrum. And from this two variables, we were also able to estimate an index that is used by modelers, which is a Benjamin Fear index, which is dependent of the pickedness parameter, the directional spread, so these parameters are mentioned here, and also what we call the significant slope, which means a ratio between significant wave height and wavelengths. And for the first time, we could produce the map of this Benjamin Fear index at the global scale over a certain period, here 13 days. And so it's very important because this Benjamin Fear index is the one used to characterize the nonlinear nature of waves and hence the probability of freak waves or extreme waves. So we are able to provide such an index at the global scale. And it's also interesting because we know that there are some limitations in the models which do not reproduce correctly the shape of the spectra because they have limitation to represent the nonlinear interaction between waves. And by providing such a quantity, these quantities of the directional spread and the frequency spread, it should be useful in the future to better understand and to improve the numerical models. Also, we can use this index to better identify the regions of wave current interaction because usually this index may be related to the regions where there are these waves interact with the currents. I will skip the bottom. Another result which is interesting also is that we have shown the possibility to extend the information from the wave height, which is given classically by the altimeter missions, as I mentioned, by using a combination of observation from the nadir beam of SWIM, from the off nadir beam of SWIM with a wave period information, and combining also with information from wind, from the SCAT measurements, which are more or less collocated with the SWIM observation, not far from the SWIM observation. And for that, a deep learning method has been tested, implemented, and validated to estimate the significant wave height at position where there is no estimate of this along track measurements. so at position of the wave scatterometer measurements. And we did this over an extended area of about 200 kilometers on each side of the track. We validated this by comparing to altimeter data, like as shown on the right-hand side. So this is the significant wave height on the extended area on the vertical compared to altimeter data at crossover points. And so you show that the comparison is very good. And so after we have checked this, this information was used again in a simulation study to show what it impacts it, to study what impacts it has in a wave model. And the result is that the impact on of the assimilation in the wave model is much more important when we assimilate this information, which is not directly measured, but estimated through this neural network, through this deep learning method. And when we assimilate this observation in this white swath area, the impact on assimilation is much more important, as indicated in this table, which is the impact of assimilation on different parameters. And you see in green where it is improved compared to the case where only significant wave height from nadir are used. So this is interesting perspectives also for other satellite missions, not only for CFOSAT, which has this specificity of both wind and wave measurements on the same platforms, but for the future, this gives idea for extending this type of method to other satellites, in particular the HY2B satellite operated by China, and also maybe to implement this kind of method for instruments which have a wide swath, like the future SWOT mission. Another remarkable results here, it's from a paper published by Chinese colleagues, is that the data could be used to estimate what we call the wave-induced stress at the ocean surface. Stress is a quantity which characterizes the exchange of momentum between the atmosphere and the ocean at the surface. And we know that within the stress, there are different components, one which is due to the turbulence of the wind, and one which is due to the impact of the waves. And the impact of the waves is not very well known. And so in this study, these colleagues tried to estimate it, well, they estimated with the CFOSAT observation. First, they used the data to separate the wind waves and swell conditions, because it is known that the impact of waves on the stress is different, whereas it's wind waves or swell. So on the left, you see the results of this separation. It's a percentage of wave energy from swell, percentage with respect to the total energy of the swell. And it's plotted for a 1 month average, different months, August, September, October, and November 2019. Here it's a zonal averages of this quantity. So the result is, well, it is already known that the swell dominates, for example, in the tropics. But here you also see the seasonal variation. And we have a very good information about this repartition, this importance of swell over all the ocean. And so this information was used combined with an empirical model which estimates the wave-induced stress depending on whether it's a wind sea or swell. And the result is shown on the right. And this is the contribution of waves to the total stress in percentage. And so for the same months, and also the zonal average. And so you see here that this percentage can reach values of up to 60%, mainly in the regions dominated by the wind sea, whereas in the region dominated by the swell, this percentage is much less. So to our knowledge, it was the first evaluation from observations, space observation of seasonal and geographical variations of the influence of waves on the atmospheric stress at the Earth-sea interface. Now I present some new perspectives, and by new perspectives I mean results that are more recent, and there are some CFOSAT data used for them, but we are still working on this, and it's just to illustrate the potential of these new types of observations. First, I mentioned, I focused on what we call wave current interaction, which is one of the topics chosen for this CFOSAT mission. And this is from a study by Maréchal and Hardouin. It's a study based on, not based on CFOSAT yet, but on altimeter data and modeling. On the top, you see in the Agulhas region, which is south of South Africa, you see the gradients of significant wave height on the right-hand plot, induced by the Agulhas current. And on the right-hand plot, it's from observation of classical satellite mission, altimetric satellite mission. The two middle and left plot are the results from a numerical model. On the middle, it is a model which doesn't take into account wave current interaction, so you don't see this gradients in significant wave height. And on the left, it's a result when you take into account in the model this wave current interaction, where you can more or less reproduce this current. But he also says that you can reproduce them only with a very high resolution in the model, here 2.5 kilometer resolution. The interesting thing in this paper was also that they showed that the distribution of wave height in this area of the wave current, of the Agulhas current, excuse me, the distribution of the significant wave height shown here is very sensitive to the directional spread of the waves. That means how the waves are spread around their mean direction. Here, it's a model result, so for a standard case of the model, and here sensitivity cases when the directional spread is increased by 30% or reduced by 30%. So you see the wave fields is modified when the directional spread is modified. This is to illustrate all the interest of the CFOSAT data, which provides this information of directional spread of the waves. To go further, and this is not yet published, it's a communication given last week, so it's very new. They look at orbits crossing this region of the Agulhas current with CFOSAT data. So with CFOSAT data and this specific geometry of rotating antenna, you see here again what the sampling. And they looked at both the significant wave height along this track, as shown on the right top plot with black lines, and compare this with a model. And you see the different places where there are important gradients in the significant wave height, which are attributed to the current gradients. And the model here, even with the current taking into account, does not reproduce this very well, this gradients, but it's under investigation. And they also started to look at the transformation of the waves in this region. And so on the right plot, it's a transformation of the wave spectrum going from south to the north along the track. And you see how the wave spectrum evolves, both with the direction and the wavelength evolving when crossing this the current region. So this is still in progress, but it shows all the interest of this spectral data. All the interest of this spectral data, because we are able to characterize not only in terms of significant wave height, also in terms of wavelength and direction in the regions of wave current interaction. This will be useful to better constrain the wave models and also the ocean wave coupled models with this observation. Maybe in the future we are going to look at this also, will be to see if we can use the signature of wave modulation as observed from the satellite as a proxy to characterize the surface current. So this is more challenging, but it's an idea to develop in the future. Among the new perspectives also, there are different works in different studies about the way wind and waves in tropical cyclones. So tropical cyclones or big storms are very specific for studying wind and waves because the space variation of wind at the scale of the tropical cyclone induce very rapid variation of the sea state at short scales also, with wind and waves which are very asymmetric from the left-hand side and right-hand side of the cyclones. So different studies have been already shown during our meeting last week, and if I summarize the results, is that we are able to better characterize the waves generated by tropical cyclones. We can confirm the phenomenological schemes which have been proposed to explain the wave fields in the surroundings of cyclones and the numerical model results. Globally, we also find with our data the asymmetry of the wave field and the wind speed, of course, in particular in the northern hemisphere. On the right-hand side of the tropical cyclone propagation, we confirm that we can see higher wave heights, longer wavelengths, and wind waves which are not aligned at all. So this means very dangerous sea states also. And the study by Yurovskaya and her colleagues, it was also to show that it is possible to use CFOSAT data to validate, simplified parametric model which are used to developed and used to explain and predict the waves in cyclones. Instead of running very complicated methods, these colleagues propose to use a parametric model which are expressed in terms of the cyclone intensity, diameter, and propagation speed, and they are able, with this some hypothesis, to reproduce the wind field and the wave fields if they can use also some information from observations to run the model. Other perspectives from the satellite, from CFOSAT data, are to analyze the waves in coastal regions. So also it's not fully appropriate to use satellite data in coastal regions. There are possibilities indeed. And this study by the colleagues from Météo France was to try to get benefit of the good quality of the nadir data with better quality with respect to altimeter, classical altimeter data, in fact, at a high resolution along the track, typically 1.5 kilometers. I will not go into details, but they compared the data at this resolution with the model data and wave model data. The model which was used has a grid and domain as shown on the left. So it's on the western coast of France in the Iris Sea, close to the Brittany region, where there are very intense tidal currents. So it's important to have precise models and also observation to better reproduce the wave behavior in these tidal environments. And what these colleagues showed is that with a high resolution observation of a swim at 5 Hertz, we have a better agreement with the model results here on the right than when we use 1 Hertz resolution. So this gives an indication that in this very intense tidal environments, it's better to use this 5 Hertz resolution. Also new perspectives regarding the polar region, because we have analyzed the signal of the radar in this polar region, the backscatter coefficient called sigma 0. And these colleagues and others have deployed deep learning method also to estimate, to relate the backscatter coefficient to different parameters in the marginal ice zone. So they could provide an empirical model which describes this behavior of the radar cross-section with incidence depending on different parameters, among which the wind speed, the significant wave height, and the sea ice coverage. So they established this method, and the validation has started, and now we are looking at all the potential of the results when trying to inverse the information to get not only the ice coverage, but probably also the properties of ice in this region. So this is under progress yet, but it's very encouraging that we are able to classify our data according to the sea ice coverage. Also, I will not go into details, but here are the results on the variability and trends in different publications. So we know there are the IPCC reports that there are only few studies which have focused in the past on wave directional change, although it's important for shoreline response. So it's important to give the possibility with observations to study the evolution of the wave spectra in the open ocean, because waves are then propagating to the coast. And these are examples of the wave spectra change in the North Atlantic from models which indicate how it evolves from from regimes of positive or negative oscillation of the North Atlantic oscillations. And you see how it evolves from negative to positive, from left to right, and in different places. So you see that the wave spectra change a lot from the models, and it would be good if we are able in the future to characterize this also with data. Maybe I will pass this. It's about trends, just to say in a few words that waves contribute to sea level variability and sea level rise at the coast. This is known by what we call the wave setup and the wave swash. In this study, these authors have shown that the wave setup may dominate in the signal, in the variability signal, in some regions at least. And within the signal of waves in green, the swell, which is in orange, which is in red, may also dominate. So it's important to have a better information on the directional, on the type of wave, and so separating swell and wind sea as is possible from our measurements. A few words about CFOSAT operational use and application. So I mentioned earlier assimilation studies, which is research, but now, because we had very interesting results, Météo France in France, the Met Office in France, decided to assimilate CFOSAT data in an operational way. So this is operational since February this year, 2021. And so this is just to mention that it's very interesting also on an operational point of view. And this shows the difference of significant wave height with and without assimilating swim spectra over the period of 2 to 10 February 2021. And on the right, you see the importance of a good prediction from these models, here illustrated with a significant wave height, which is more than 7 meters in this region of the Southern Ocean, which hits the coast of Madagascar and La Réunion. And so it's very important to have a good prediction in this region. And this is increased. The prediction is better if we can assimilate data in this region in particular. So now to finish with, I'd like to mention for users that there are several ways to get access to the data. One is to go to this address, the Aviso Center, which is under the CNES responsibility. We also distribute the data to EUMETSAT, who make accessible the data to member states via the EUMETCAST system. Until now, it's only SWIM, but it's under discussion that they could distribute also the Chinese CAT data. We also distribute data to the Copernicus service in Europe. For the moment, it's limited products, but it is planned to enlarge the information provided to Siemens, to the Copernicus service. So in conclusion, I should say that I tried to convince you that CFOSAT is an innovative satellite mission The first one, which is entirely dedicated to wind and waves at the surface, ocean surface. It has novel instrumental concepts which demonstrated their performance. It's the first French-China cooperation in space science. And we have already scientific breakthrough in the first 2.5 years, and it is remarkable, counting for the fact that really it's really new system, and the data are widely accessible. So this is my talk. I will not go to the...
Thank you very much, Danièle, for this very rich presentation, interesting and rich. And we have time for a few questions. So to the participant, you can either raise your hand using the icon on the bottom of your screen, or write your question into the chat. So I see that there are already questions in the chat.
It's a long question.
You see it, so it's, yes. Okay.
A comparison of wavelengths, there appear to be stripes at some model wavelengths. Is this understood model or instrument effect? Yes, partly model, I think. At the time where we did this comparison, there was still tuning in the models, which assimilates also SAR data. And so there was some, we think this effect is partly due to the model. And we are going now to do a new comparison with a model which has been corrected now.
The second question is from Rodrigo Abarca del Rio. So do you see it?
Yes, in many countries in the southern hemisphere, for example, in Chile, renewable energies are to replace all fossil energies, etc. So therefore, the results of this mission are very relevant for the national objective. They cooperate. I don't know where are the question.
I think
how
it's
to participate more actively.
I think it's to use the energy of waves.
So how to, I understand that the question is how to participate more actively. What, for example, is possible for teams outside France and China to participate officially in their validation? First, you can have access to the data whoever you are for research. And so I have given the link to access. So even if you are not referenced in the science team, you can get the data and start looking at them. And we are, of course, we are ready to give explanation if necessary. And then also I must say that probably there will be a new issue for the constitution of the science team next year. So this will be confirmed, but and in this case, you can join officially the science team starting next year. And anyway, if you have a collaboration with one of the team who is already looking at the CFOSAT data. So for example, if you have already a cooperation with Météo France, you can have contacts with them and we can include you in any case.
Danièle, you have also several questions from people who are raising their hands. So maybe you want to briefly answer the question in the chat, and then we shift it. Okay.
Okay, I see one from Hans Zinnecker. Yes. What is the average water evaporation over the ocean? Oh, I don't have a number, but it's important. Sorry, it's a little bit different subject. Okay. Craig Donlan, I guess, at CMEMS appear to be using CFOSAT data. What plans are there for an operation follow-on mission to CFOSAT? Oh. I don't know exactly. I am not in the space center from a space agency. I'm a research laboratory, so this is something which is discussed between the space agencies. I know that there are discussions, maybe in a European context, but I cannot say more. I don't know. There is no definite response on this. There was something, the scheme project for current measurements was really based on the same technique for the swim as for the swim instrument, but the scheme has not been selected. So now we have to discuss more about the perspective of a follow-on mission.
Okay, so now we shift to the question. So the first speaker, or participant who raised his hand is Giovanni Okshipinti. I don't know how to pronounce. So
Yes.
please ask your question.
Yes, do you hear me?
Yes.
Perfect, thank you. So thank you, Danièle, for this amazing presentation. So I have a couple of questions. So the first question is how the satellite manage the ionosphere. How the data are corrected by the ionosphere, and if you know if there is in the data a product related to the ionosphere, or if there is a possibility to compute the ionospheric effects that I suppose that the satellites is corrected for.
No, in fact not. There is no correction for ionosphere. We are not with the objective was really to measure wind and waves and not topography. Where indeed for topographic measurements it's very important to have a ionosphere correction and troposphere corrections. In our case, the objective is not to measure the range, the topography. So there is no correction of ionosphere, and there is a simple correction for troposphere on water vapor using model information.
Okay,
but we are not. Yes.
And I have another question, and that is maybe related. That is more related to the performance of the satellite in the sense, and the captures in the sense. So you showed that clearly that you were right to detect a lot of different waves with a different scale and different periods and a different amplitude, and I wish to know which is the possibility of that instrument to detect single wave, like for example a tsunami that have a really big wavelets, specific period. And there is maybe a possibility to use that for a specific observation with a specific filter?
As you know, for any satellite mission, so the orbit is determined by the law of the orbiting systems, and so we cannot be at the good place at the right place at the right moment. So it's a really a good chance if we cross a tsunami region. And now about detection, if we are at the good place at a good time, then detection, I am not sure we will be able to see it, but it's difficult to give a definite answer because I don't know the exact slopes of this kind of waves. It mainly depends on the slope of the waves, of this kind of tsunami waves.
Danièle, we have two more questions, and I think after that we will stop. So the next one is by Guy Brasseur. So Guy, please.
Yes, hello. I was very impressed by the new capability that exists for research based on what I think is a real game changer. But I would like to ask a little more about the operational perspective for such a satellite. So you mentioned at the end of your presentation that Météo France is going to use some of the data. Do you see the possibility in the future that near real-time data will be available to any meteorological center in the world that could use this data to improve essentially wave prediction, forecast, and be of direct help, for example, for the maritime traffic. So do you see a real game changer also in the operational world?
Yes, maybe I was not clear in my talk about this. Indeed, CNES already provides the data in near real time. That means in less than 3 hours after observation. And so the data are processed in near real time also to the EUMETSAT. So at the European level, because this is our agreement with Chinese colleagues for a moment. You hear me?
Yes.
Yes. The agreement between French and China is on the transmission to EUMETSAT, and EUMETSAT can provide this to all his members of EUMETSAT. And we are discussing, CNES is discussing about the possibility to extend this to more widely around the world using the WMO system.
Okay, thank you.
So next question is by Gilles Someria, and I don't know if there are questions in the chat.
Hello, Gilles.
Gilles?
You hear me now, no?
Yes.
Ok,
Yes.
bon, bonjour à toutes les deux alors. Je suis content de vous avoir. Okay, I was very impressed by the talk as well. And you showed, Danièle, interesting results on the momentum fluxes. Are there ongoing studies or similar results for CO2 fluxes, for example, or heat fluxes on scalar quantities?
Not,
Important.
I don't. Yeah, there are from in situ measurements, sure. From satellite measurements, I am not sure, but of course, if the coefficient of exchange have the same sensitivity to dependence with sea state, it could be possible to do this for other fluxes, of course.
Okay, but you are not familiar with ongoing studies on that yet.
Not with space observation. I'm not sure that it's done. It depends on the parametrization, in fact. So it's very dependent on the parametrization, and if we can use wave data within the parametrization, then of course it will be possible.
Okay, so you have another question? No. So I think we need to stop now. Thanks again, Danièle, for this very interesting, as I said, very rich presentation.
Sorry, I was a little bit long, but
no, it was fine, and it is recorded, and people can see it on YouTube in the future. I think as soon as tomorrow. And thanks to you first, and thanks to all participants, and bye bye.
bye bye.
See you next time.
Thank you to